manufacturing technologies that we have dealt with. And I would like to share with you the slide by the setting. So this is the technologies which is somehow similar to the Parabet fusion, similar to. So this is the combination of Parabet fusion with material settings, in which the powder will be laid down on the platform to form the layers of powder, so even layer of powders, or the powder with uniform thickness. So we would like to have the uniform thickness of the coating layers, yes, in order to guarantee their even thickness of these layers. The printed head can contain a single or multiple nozzles, which can pass through the powder bed at the given head. And during this time, the print head will deposit the droplets of part binder. So this kind of depositing a binder onto the powder's layer. And once the layer is formed, the process is repeated until we form the 3D part. And you may have in mind that once the process is completed, we have the part is surrounded by the loose powder. And we can consider with two different kinds of materials. So polymeric materials and metallic or ceramic materials. So let's simply consider here polymer and metals, which are the two most important materials that can be used in the field of, let's say, aerospace industry. Yes, ceramic, yeah, we still have some kind of applications, but not so popular in the field of, yes, except for the coating. For example, thermal barrier coating, they use the ceramic materials, but I would say that is not so, it's not as common as the case of metals or polymers. So for polymeric materials, after the process is completed, the part do not need post-processing, so we just leave the part there. However, in the case of metals or ceramic, we need to remove the binder, because it's the binder is just the substance which you to combine or to bond the material together. However, the binder has relative low strength with respect to the surrounding materials. I mean metals, and therefore it is necessary to remove this kind of binder by heating the pot at the sintering temperatures in order to promote the solid state diffusion. So diffusion is mean khuếch tán in Vietnamese. So it means that at the high temperatures, the atoms of the material receive the free gift energies and it can move. Yes, and during this moving process, we call diffusions, and these material will have better connection between them and provide higher strength material. However, since we already remove the binder materials, and therefore the process create the porous structures. Porous is mean that we have a lot of free volumes inside the metallic materials. So with the porous form, of course, the material will have lower relative density. So should be smaller than 1. And this is unexpected. And therefore, we need to apply another post-processing steps in order to improve the density of the materials. So for example, using the HIP, for example, it stands for hot isostatic pressing. It means that you apply high temperatures, high pressure, and then the part will be deformed. And then during this process, the void or the free volume inside the part will be eliminated and improve the strength and the density of the materials. Or in with another approach, you can use the infiltration process. Infiltration in Vietnamese is called kind of thẩm thấu. So it means that you use the second materials with high concentrations. So inside the part with 0 concentrations, so we have the deviation of the concentration. So material at the preferable conditions when we move from the position where we have the high concentration to the area where we have the low concentration. And this is the process in order to improve the density of the material. So the second material will infiltrate to the free volume inside the base meters. So in doing this, you can improve the strength and the density of the materials. So that is the idea of the process. So if you can see from the figure on the right side, on the bottom right of this slide, you can see that on the left side of the figure, we have the powder feeder systems. So the powder will be supplied via the leveling roller and deposit the material to the let's say building chambers above the substrate plate or the building plate, so whatever you have. So once a layers of powder is formed, and then the printed head will deposit the inset or the, the binding substance, yes, the binding substance or the binder, in order to connect the powders together. And afterward, yes, you have some kind of green part. So if you have studied the ceramic, you have the green part. So you need to apply the sintering temperatures in order to remove the binder in the case of metals or ceramic. And afterward, you need to apply another processing steps in order to improve the density and the strength of the materials. So for example, hot isostatic pressing or infiltration. And that's the point. And now I would like to show you, okay, step-by-step 3 video clips regarding the binder zetting process. So just a few seconds. First, I have to open it firstly. Come on. So hopefully that everything is going to be fine. Advertisement, yeah, usually skip and then stop. Yeah, share with you. That's it. Okay. So I do not open in full screen mode. So just to control my screen, otherwise it's quite difficult in order to see what I'm doing at the moment. So as you can see that X1 is the branch name of a company which provide, yes, additive manufacturing solutions. So one of them is the binder zetting machines. So this kind of light system, so it's not only the a printer, but it's something like a system. So the printed head, it's comparing the foundry processes in some kind of dupe, yeah, foundry or casting. Design for high complexity, so it can be used in order to design and fabricate the highly complex part. Yeah, especially the lattice structure. So we have different kind of strut lattice inside the skin. So we have the skin carrying outside, and then we have the internet support structure or internet lattice. So the machine will deposit layer by layer the materials. So the powders material together with the binder in order to bind them together or to connect the powders together. The bonding process actually. Yeah. So here you could observe the some brief working principle. So we have starting from the CAD files. So how to arrange the CAD file with respect to the building substrate. Yeah, we have the position of the materials and the binder to the substrate. Yeah, so we have the powders. And once the powder is are deposited to the building plate or the previous layers, and then it is necessary in order to coat to deposit the binding substance just onto the area that we need to, just onto the cross sections. So we have the multiple nozzle here to deposit the droplets of binders, to connect the powders together. So you can see that The process runs. Oh, and just the cross section defined by slicing process defines, and then you have the cross sections and the print head. We deposit the droplet just onto the area of the cross section of the part. So this is possible, to build multiple parts at the same time. So it depends on the size of the building chamber, and it's repeated. The process is repeated until we build up the 3D part. So this is a powder removal process for recycling, probably. So please keep in mind that this kind of powder is extremely detrimental to human health. So you need somehow safety device in order to work, in order to handle with these powders, especially the metallic powders. So previously we have talked about the graph, and it's compatible with the small series productions. Yeah, and there's possibility to apply to fabricate the parts that can be used in aerospace industry, of course. So the idea is to fabricate near-net shape part, and in doing this, you can save a lot of materials. Yes, and you can fabricate the highly complex parts for the advanced applications, and therefore, it's quite great technology. Okay, so now let me show you the second video. Oh, come on. Just a moment, because the guys which attended the course of aerospace material still asked me the link in order to study the additive manufacturing. However, the guy just enrolled for the course of aerospace material, so I do not know why he just contact me frequently in order to ask the link on Thursday. It's quite unreasonable. Okay, forget about this. It's not suitable. Let me show you the second video. Stop here. Where is it? Okay, here. So still another video which made by X1 company. Yes, but we see the process. So starting from the motors, 3D 3D printing motors. So basically, if we talk about this process, and normally we have to generate the motor by the software. You can use the software which is compatible with the 3D printers in order to prepare the ready-to-print motor. But at the same time, the printer equipped with another software, we can somehow work with this motor to provide some kind of a modification if necessary prior to the printing process. And for the new system, so it is quite convenient for the technician in order to remove the building chambers. Yes. So this is the new system, which helps the technician in moving these heavy parts. Yes. Yes. And afterwards, we can use the vacuum machines, to suck all of the residual powders. Or here they use the term the powdered or the cleaned from the powders, and can be prepared for the next step. Yes, if it is the metal or ceramic, because you know that if it is metal polymeric materials, and we can left the part here, but it is made of let's say metals or ceramic, and we need the infiltration, as we need to build the channels in order to move to promote the diffusion of the second material to the part. Yes, so we need the channels in order to diffuse the second materials. For sure, at the high temperatures and at a certain pressure, so that the second material will flow from the area with high concentration to the area with low concentration, and to improve the and to film the porosity inside the part and improve the density of the part. And in doing this, we can improve also the strength of the materials. So you can see that, for example, this is the copper, which can be infiltrated, yes, to the part. Yeah, sự thấm infiltration. But with this kind of technologies, so we still have the material inside the flow channel. So similar to the casting process, so it's not really safe materials, because the second material is somehow stored in the channel. But comparing to the traditional manufacturing process, for example, cutting, you still save a certain degree of second materials. So it depends. Yeah. So everything has two sides effects. So you are often some benefit on the one side, and on the other side you may have to pay a certain expense. Okay. And now I would like to show you the third video. So, here. Advertisement. That is coming. Yes. Still another video is from X1. So many consider additive manufacturing is the future technologies, because we have talked a lot of the sustainability advantages of additive manufacturing. So, and we have a wide range of the areas that can use additive manufacturing as the promising fabrication technologies to fabricate the real parts. There's somehow a history of the development work for this kind of system. So up to more or less the time that they see this video. Yes, so you see that the recorder or the recording device or the recording blade, and you have which deposit the materials as well as the binder onto the substrate or onto the previous layers. Yes. And the process is happen inside the box, and this is possible in order to remove the box. Yes. For the next printing, for example, to create another part without stopping the whole system. So we just remove the breathing chambers and we continue, yes, the works for the other parts. Vertical jacket. So the speed is relatively high, up to 135 liters per hour. So 18 seconds per layer. And please remember, for each layer, we need to deposit both the materials and the binder. So I think this is the future concept of the company, where everything can be worked and supported by the, let's say, automatic system or robotic system. Yeah. So starting from the process of 3D printing, the green parts, up to the process of post-processing, like, for example, hot isostatic pressing or infiltration. Okay. So it's the future, yeah, technologies, but probably several large company in the world may already applied this. But, to be honest, it's not really popular for the moment. Okay. So now let me stop and continue with the slide. Okay. By the setting. Okay. So the last but not least technologies are among the seven additive manufacturing technologies called direct energy depositions. But as I already mentioned to you, despite the fact that it is one technologies, but inside these technologies we have several kind of sub technologies. Yes. So generally speaking, is a group which contains several kind of small technologies. Yeah. So the idea is that you deposit the material spot by spot, line by line, and layer by layer. And during this process, for export, you deposit the materials, and you still have also the irradiation of the heat source to locally melt the material, especially with the metallic powders. So the part will be built spot by spot. So you can see from, for example, electron beam freeform fabrication here. So this kind of wetting process, where we have the heat source irradiate in order to provide the, the, the energies, to heat up the material up to the melting temperatures. Yes, to create a melt point. And once the gun, the electron beam gun or the wire feeder, move to the next positions, so the previous position will be cooled down for sure, and the material will be solidified, and to connect with the previous layer, and to connect with the deposition line. Yeah. And here I would like to highlight some points. So for example, process. So we have the raw material is deposited directly to the locations, where we also have the energy input. So the deposition of material at this point, and at the same time we have the irradiation of electron beam, for example, or the irradiation of the laser. Yes, as the heat sources. Yes. So in other words, we have the energy input and the material deposition site are co-located. So at the same position, And we have different subcategories called lens. Also, we have the definition of lens here. Is the brief name of laser engineered net shaping. And the other EBF3, so is stand for the electron beam freeform fabrications. So the heat source is electron beam gun, and we have the wire feeder. So it depends on the technologies. The heat source can be the electron beam or the laser, or even the plasma, And the feedstock material can be the powders or can be wire. can be wire. Or we can have also the other technologies, namely arc additive manufacturing. So wire arc additive manufacturing. So the feedstock material is wire and use the arcs for quang, yes, at the heat source in order to additively manufactures the part layer by layer. So these technologies, lens, ABF3, wire, and arc additive manufacturing have similar working principle. But for sure, they employ different energy sources and different kinds of raw materials. So the energy sources, as I already mentioned to you, can be the electron beam, can be the laser, can be the plasma. Whereas for the raw material, this can be in the form of wire, so cái dây, wire, or powders form, So a little bit more detail about the laser engineering net shaping. So the powder is injected into the spot on the surface here. For example, the powders. So we have the two channel, which can be used in order to deposit the powders material onto a spot on the surface. This can be the surface of the substrate plate, or it can be the surface of the previous deposited layer. Yeah, for sure. It depends whether it is the first layer deposition or it end layer, which with n is larger than 1. Yes, it's just the number of the layer that the system is dealing with at that time. So first, the powder is injected into the spot on the surface together with the laser beam, because we need to apply two factors at the same time. One is the material, and second is the heat source. So the heat source will be irradiated to the spot, and the material will be deposited to the spot on the surface. Yes, and in other words, we add the material to the surface, and with the application of the heat source, the material will be melt, yes, or fuse in order to build the part. And as I already mentioned to you, the part is formed spot by spot, line by line, and finally layer by layer, and we repeat the process so that the 3D physical objects can be formed eventually. For the just a moment. For the wire arc additive manufacturing, the metal wire is fed into the melt pool, and the process is combined with the automated metal inert gas wetting process. Yes, in order to create 3D part with the wet lines. So simply speaking in Vietnamese, so đơn giản là đối với cái wire arc additive manufacturing thì các bạn sẽ sử dụng cái metal inert gas này như là một cái quá trình hàn để hàn các cái dây kim loại, đúng không ạ? Hàn các cái dây kim loại, và chúng ta cứ hàn từng cái đường hàn một, và đường hàn nọ nối tiếp đường hàn kia để tạo thành các cái lớp vật liệu. Và sau khi từng cái lớp vật liệu đã được deposit xong thì người ta sẽ tiếp tục deposit các cái lớp thứ hai. Và tất nhiên cái deposition này thì cái việc deposit vật liệu này thì nó chỉ nằm trong cái giới hạn của những cái vùng mà define bởi cái quá trình slicing process bằng cái software. Có nghĩa là chúng ta define trước cái cross section, đúng không ạ, là cái vùng nào nó sẽ được deposit material, đúng không ạ? Thì quá trình mà cái đầu laser hay cái đầu tia electron beam này, cũng như là cái phần đưa cái kim loại dạng powder hay dạng wire đến, thì nó cũng chỉ quét qua những cái vùng mà cần deposit vật liệu thôi. Do vậy mà nó đem so sánh với cả cái phương pháp Parabet Fusion thì rõ ràng cái phương pháp này nó còn tiết kiệm vật liệu hơn, và cái vật liệu nó ít bị ảnh hưởng bởi nhiệt hơn là so với phương pháp Parabet Fusion. Bởi vì đối với phương pháp Parabet Fusion thì sau khi mà chúng ta coating cái layer powders ấy, chúng ta coat không chỉ ở trong cái vùng mà laser nó sẽ scan qua, mà chúng ta coat cả trên cả cái diện tích của cái building plate, đúng không ạ? Thế thì những cái vật liệu, những cái residual powder, có nghĩa là những cái powder mà không bị thiêu kết ấy, thì nó sẽ bị ảnh hưởng bởi nhiệt. Đấy, thì cái đó, cái gì mà đã bị ảnh hưởng bởi nhiệt rồi thì nó sẽ bị biến đổi cơ tính, bởi vì nó là cái quá trình heat treatment. Đấy, cơ tính thường sẽ giảm xuống. Như vậy nếu mà chúng ta tái sử dụng những cái anh powder đó thì cái cơ tính của chi tiết sợ rằng nó sẽ không đảm bảo, đặc biệt là những đồ bên chi tiết mà yêu cầu cơ tính cao, là người ta không prefer dùng cái residual powder sau, hoặc là gọi là overflow powder cũng được. Thì những cái đó là phải chúng ta phải cân đối. Ngoài cái yếu tố mặt kinh tế, rõ ràng là chúng ta tận dụng được cái residual powder rồi, nhưng mà cái yếu tố về chất lượng thì chúng ta cũng phải xem xét ở trong đó. EBF3, electron beam free-form fabrication. So the working principle is combined between the laser engineering net shaping, and the wire arc additive manufacturing, in which we use wire feed system to introduce the wire materials. And during this deposition of the material, we use the electron beam as the heat source, yes, in order to melt locally melt the materials and deposit onto the substrate plate or on the previous layer. And this process is performed under the high vacuum environment. That's because we use the electron beam gun. So if we have another kind of substance, like for example, another gas phase or another gas items which is flow on the way of the electron beam, and these atoms will, how can I say, will reflect the electron beam and reduce the energies of the electron beam gun, and if the energy is not enough and it cannot totally melt the powders. So this is one of the things, and this also affect the quality of the part, and therefore especially for the electron beam melting process, and we need to maintain the high vacuum inside the building chambers. Or the other, yeah, but in general, I would say the direct energy deposition is suited for repairing a large mechanical or structures components. So if you could see from the repairing process for the impeller pump here, this is the position the material onto the impeller and be onto the blade. Let's say, for example, if you consider the shaft which have the cylindrical shape, and if the shaft is working with bearing. So for example, if you have the bearing seen at the support for the shaft, so we have the friction between the two surfaces, the external surface of the shaft and the inner surface of the bearing. So even if you have some kind of lubrication, to reduce the friction, to reduce the wear, but you still have some kind of wear. Yes, you still have some kind of wear. It depends on the quality of the lubrication. It depends on the working regime of the shaft and so on. But generally speaking, we still have wear. And if the wear is occur and the external surface of the shaft will be worn, and we lost of the materials, and the diameter of the external surface, the diameter of the shaft will be reduced at the area which is come into contact with the inner surface of the bearing. And the solution in order to repair these structures is to use the direct energy deposition in order to deposit the materials on the surface, on the worn surface of the shaft. Yes, so we have the process of adding the material onto the worn surface, and afterward we use the turning process in order to cut the residual material and to generate the high quality surface. Yes, by using turn cutting. Yes, cutting and then polishing. Yeah, cutting, milling, and polishing. So we have the new shaft, which can be repaired by direct energy deposition. So let me show you the two video clips regarding the direct energy deposition here. So let me show you. So you can see the working principles of the process. So we have two channels which can be used in order to deposit the material to the substrate. And in the middle, we have the channels which can be used to irradiate the heat source. So it can be, for example, electron beam or the laser. And once the material is deposited onto the surface, and at the same time we can irradiate the heat source in order to melt the materials. And this process is quite a little bit complex, because we have to control not only the head printer, let's say, but also the substrate. Yes. So one of the disadvantages of the process is just can be used in order to fabricate one part at a time. So comparing to the case of bidesetting, for example, or in the case of powder bed fusion, where you can fabricate multiple parts at the same time, but for the direct energy deposition, just one part at a time. So the final part has almost similar shape with respect to the the 3D printed part has similar shape to the final part. So afterward, you may apply the post-processing in order to fabricate the final part, or you can leave the print part there. In other words, we save materials. So we do not need to cut the materials afterward. In some cases. And if you need to have the high quality surface, and for sure you need to deposit a little bit more materials, and afterward you still have a certain material in order to cut and to finish the part, yes, with the higher dimensional tolerance or with the higher quality, yeah. Or low average roughness on the surface. Yes, and the second video, let me show you here. So I'm still sharing with you the video clip regarding the direct energy deposition. So the second system is provided by the DNG Mori, which is one of the German company. Those can provide additive manufacturing solutions to industry. So we have the laser, the laser beam in the middle, and we have the two channels we can be used in order to fit the material to the substrate or to the previous layer. So it's possible to build up the thin worn structures with the thickness of the worn is range from 0.1 up to 0.5 millimeters. So it is quite thin, I would say, as introduced by the video. Yes. So after the process, yes, in order to have the higher, in order to create the higher quality, higher surface quality, and you may have the milling process in order to smooth these kind of surfaces. And because you know the average roughness of the 3D printing process is relatively high comparing to the traditional manufacturing process. So if you want to have the higher qualities of the surface of the printed part, and then the post-processing step are necessary to apply. And for DMG Mori, the company can provide very complex systems where you can combine, or you call the hybrid manufacturing, and it can combine both the additive manufacturing system and the CNC system, so that after the 3D printing process, you can directly apply the post-processing like cutting, drilling, milling, polishing in order to improve the surface quality of the parts. Okay. So now I would like to continue with the slide. So you can see that today is the fourth day of the course. We have more or less 8 days, but we are still now at the chapter 1 because you could think of how important the chapter is. It provides you the overview about the additive manufacturing, and afterward, yes, you will study in a little bit more details about the parameters of the additive manufacturing, about the materials, about the designing process. And however, for each group of students, so they just focusing on one technologies and try to prepare the report for one technologies only. So that's why I would like to focus a little bit more on the chapter 1 because it's quite important. The idea why you should study the course. How many technologies do you have for the additive manufacturing? I mean the subcategories of additive manufacturing and different kinds of advantages and disadvantages when applying additive manufacturing in industries. Yes, don't worry because okay. So some advantages of direct energy depositions. So similar to the case of particle fusion, so the direct energy deposition we also consider with the two kind of heat sources, or maybe the three kinds, or maybe three kinds. But let's say if we consider the laser as a heat source, or on the next slide probably you will consider the electron beam as heat source, and we are mostly talking with the metals here. But if you are interested in technologies and you could find more information with the direct energy deposition, working with polymeric materials, for example. So that's possible in order to work with multiple powders or wire feeders. Yes. And you can have the ability in order to change the material composition during the deposition. So there's not a restrictions. So the technologies can not only be used in order to fabricate the part, but it can also be used in order to repair the part. Because you know that is some kind of welding process. So if some surface is worn, and you can deposit the material onto, cut and polish in order to repair the parts. So no problem. So it offers a large and flexible build chamber. Yes. So comparing to the case of particle fusion, direct energy deposition can be used in order to fabricate larger part than in the case of applying particle fusion to fabricate parts. So the technologies can use several commercial available metal powders or wet wire filler materials. So if there is possibility to use the wet wire fillers materials, so you may save costs, and there is possible wider range of certified powders or wet wire, especially if you use the wire, because the cost of the wire is cheaper than the powders. It's quite difficult in order to create the small powders which have similar size, which have the regular shape and similar size. Yes, it's quite difficult. And how to store appropriately the powder is also important, because otherwise the humidity will have a negative influence. The oxidants, the oxidation process will have a negative influence on the quality of the powder. And therefore, if we use this type of powders as the feedstock materials, and of course, it have the similar influence on the final quality of the 3D printed parts. Repair, yes, of course. These technologies can be used in order to repair, to remanufacture the existing parts. Yes. Finishing in process inspection and can be handled on a machine. Yes, so there's no problem. So you could have the brief summary in the figure. Yes, where the figure highlights 5 different advantages of the laser directed energy deposition. So I will not talk about this again. And the opposite side of using direct energy deposition with laser as a heat source. Yeah. So we have several limitations as follows. So first, regarding the software, yeah, because it's not only control the head, where we have the deposition of the materials, where we need to control also the heat source irradiation. So, for example, the laser irradiation or electron beam irradiations. But we also to have control the substrate plate. So as you can see that the substrate plate can rotate. Yes, yes, can rotate, but in different directions. Yes. So if we consider the rotation axis, for example here, so the rotation axis can tweak, can rotate. Yes, and therefore is more complex to control the part for the depositions. And yes, this is one of the limitations. So the more complex the control is, and the generally speaking, the more difficult you you could have the high quality part, because easier control, so it's easier to have the higher quality part, but more difficult to control, and it's quite it's quite hard in order to have the good quality with respect to the case of easier controlling. It's difficult for the powder recovery or recycle chamber cleaning, because the beam chamber is large comparing to the case of the powder bed fusion. Yes, so it depends on the system, because for powder bed fusion system, so they design what can I say, the subsystem in order to collect all of the residual powders for recovery or recycling. But in this case is different structures, and therefore they did not design, yeah, or it's not reasonable to design this kind of system in order to collect, to recover or recycle. How to achieve the desired dimensional accuracy? Yes, for sure. Yeah, there's many things that affect these factors, I would say. But generally speaking, comparing to the case of powder bed fusion, direct energy deposition will be used to fabricate the parts which have a lower dimensional accuracy than comparing to the case of using powder bed fusion. And seeing the process tend to create a larger molten pool. Yes, it means that we irradiate the heat source onto the material. The material will melt and create some kind of molten pool, một cái vũng lọc, một cái vũng kim loại lọc. Yeah. Since we have the large molten pool, the solidification and the shrinkage stress lead to the formation of high residual stress and part distortion. Yes, and because the larger these areas, so so we have the larger thermal gradient between this area and the other area of the part. And this thermal gradient will be considered as one of the reasons promoting the residual stress. And if the stress is released, and we have the part distortion. So we may have the part distortion. Heat buildup is hard to attract. So if you could see from one of these videos that I have shown you, so most of the direct energy deposition process do not, I would say almost all, but not all, do not require support structures. So you see that the material is deposited onto the substrate plate, and there's no support structure outside. So just the part attached to the building plate, and the part is built up layer by layer, and that's all. You do not see the support structures. Generally speaking, the support structure can be seen as the means to dissipate the heat during the building process. And seen in direct energy deposition process, you do not have the support structures, so the heat buildup during as a consequence of applying heat source. Yes, you have the heat buildup, so it's hard to attract. Yeah, it can be dissipated through the environment, the surrounding environment, but surrounding environment for the case of vacuum, so is the environment which not promote the thermal, how can I say, heat dissipation, and therefore the heat will be stored inside the part. The heat can be dissipated through the substrate plate, but since we do not have many support structure outside, and then comparing to the case of particle fusion, the heat is harder to extract. So since the heat is hard to attract, the temperatures of the part is high, and it promotes the atom diffusion process, and therefore the grain can be grow, and can grow. The grain can grow, or it can promote the segregation of metallic impurities. And as the consequence of these effects, so you may have the formation of undesirable phases, defects, and distortion. And therefore, this is some main limitation of the direct energy deposition using laser that you need to consider. Okay, so now we will have 10 minutes break, and we will resume the class at more or less 2 past 1. Okay.